And so I think, yes, we are recording. Works?
Okay, perfect.
Thank you. And I can share my screen now. Thank you very much, James.
All right, see you.
See you. So everybody can see my slides, right? And we are recording. Okay. So, let's get started. Sorry. Can you see my slides clearly? Because I have interference with the Zoom. Like the Zoom window is overlaying the technologies. Okay. I don't know what's going on. Okay. Okay, stop share. Okay. How do I move that? Sorry, do you see my slides, or Zoom is overlaying the window as well? Because I don't know if it's on your computer, you see only the slides, or there is a window, Zoom window blocking the view.
You can see the slides.
It's fine.
So there are only slides, or you can see Zoom as well?
Slides only.
Say it again.
Yes, you can only see the slide. Like
Okay, cool. Because on my screen, there is Zoom window, which is blocking part of the screen. So I was wondering whether it's bothering you, but if you see only slides, because I selected sharing only slides. Cool. So yeah, let's get started. So today I'm going to talk about detection of gamma rays at lower energies. So before previous lectures, Natalia told you about detection of gamma rays with energies above, say, 100 GeV. So today we're gonna talk about detection techniques of gamma rays with lower energies. And well, you probably heard that gamma rays, it's the photons with energies above more or less 100 keV, 500 keV, depending on the definition, but okay, more standard one is 100 keV. So below that is X-rays, and above 100 keV, we've got gamma rays. And the detection technique used to detect the gamma rays is depending on the way the gamma ray is interacting with matter. So due to different, so a photon with different energy will be interacting differently with the matter. One of the reasons is the wavelength, you know, the shorter wavelength. So the waves with longer wavelength, they can bypass obstacles. So the shorter is the wavelength, the more is the probability usually for the interaction. So on this plot, you can see the attenuation of the gamma rays depending on the energy. So the attenuation is in these units. So it's the cross section of interaction per gram of matter. So more or less, what's the total cross section in the per unit of mass. And this is, I think it depends on the material, but I think it's for lead. So, and the x-axis showing the energy in MeV. So the gamma rays, they start more or less with, as I said, 100 keV, so 0.1 MeV. So it's somewhere around here. I don't know if you see my cursor. Yeah, I hope so. So here are the gamma rays, and below these are energetic hard X-rays. So the gamma rays with the lowest energy, around 100 keV, they interact via photoelectric absorption. What is that? So it's when the gamma ray is hitting the atom, it knocks out the electron, so the electron is kicked out, and you get ion and electron, and this cross section is declining with energy. The higher is the energy, the lower is the probability of the interaction. It drops as the energy -3. So at some point, the total cross section for the photoelectric absorption starts to compete with Compton scattering. So the gamma ray is seeing the electron in the atom more like free rather than bound. So the shorter is the wavelength, the more localized is the wave, let's say, if you can consider it as a wave. And so the photon doesn't perceive the atom as the whole structure, but rather sees the nucleus and the electron separately. So the wavelength, the gamma ray with high energy rather interacts with atom separately with the electron and with the nucleus. So it interacts with the electron as it was free. So it starts to interact via Compton scattering, and this is just, let's say, it's the scattering of gamma ray on the electron. And in this process, the photon transfers part of his energy to an electron. So electron gains some energy, and yeah, this is called Compton scattering. And at higher energies, so you've got Klein-Machine effects. So it's when the cross section starts to drop more or less as logarithm by the energy, and at some point it starts to compete with the pair production. So when the Compton scattering efficiency drops at around 10 MeV, the pair production starts to be more important than the Compton scattering. So Compton scattering is dominant in the energy range from 100 keV to 10 MeV, more or less this range. And above that range, so the photon above 10 MeV, when entering the matter, it produces the electron-positron pair in the vicinity, in the Coulomb field of the nucleus. And obviously for that, the energy threshold has to be surpassed. So the total energy of a photon has to be higher than twice the rest energy of electron, which is 511 keV. So you need at least 1 MeV to produce electron-positron pair. So the pair production, you see, it has a sharp cutoff at low energy around 1 MeV. So below 1 MeV, this process is impossible, and then its probability is growing. And at higher energies, the probability or the cross-section of pair production is more or less saturating. So you have the cross-section, which is constant and doesn't depend anymore on energy, and is more or less fixed to, let's say, you can see it depends on the cross-section. It depends on the nucleus charge, but okay, I'm going to show the formula later on. But yeah, so you see three different regimes of interaction. So photoelectric absorption, Compton scattering, and pair production. And so the way you're gonna build your detector to detect gamma rays depends on this process. You're gonna use different techniques. So now I'm going to talk about detection of gamma rays using above 10 MeV. So from 10 MeV up to 100 GeV or more. So using pair production process. So above 10 MeV, so this is called Bethe-Heitler pair production. So a gamma ray entering matter, it interacts with the Coulomb field of atomic nucleus, and it is converted into electron-positron pair. So a gamma ray on its own in a vacuum cannot oscillate into electron-positron pair, because if you write trivial energy momentum conservation formula, you will find out that energetically this is possible, but you need a third body to grant the momentum conservation. So this process is impossible without a third third particle, let's say. And the third particle, in this case, it is the virtual photon provided by the Coulomb field of the atomic nucleus. So this is the let's say the third body, or third particle, which is required to preserve the momentum conservation law. And so you need either, so there are two ways you can produce electron-positron pairs. So either one single photon is interacting with a nucleus, or you've got two photons, two gamma rays, which are colliding, and you have electron-positron pair. So here I focus on the interaction of one single gamma ray with the atomic nucleus. So a gamma ray, which is colliding with the atomic nucleus, is converted into a pair. And the cross-section of this process, so this is proportional to the z square, to the square of the charge, and the sigma Thomson is the Thomson cross-section. But as you can see, so this is the Feynman diagram. So this is how the interaction proceeds. So there is a gamma ray, and it interacts with the virtual photon provided by the nucleus. And so you have electron-positron pair, and you have three vertices, so 1, 2, and 3 in the Feynman diagram. And the rules of quantum electrodynamic perturbation theory, they say that the cross-section of the process is proportional to the fine structure constant, which is electromagnetic coupling constant, in the power of the number of the vertices. So here, so if it's a Compton scattering, so you have only two vertices. So you've got alpha square, which is sigma Thomson, but here you have three vertices, so it will be the Thomson cross-section multiplied by 1 time the fine structure constant, which is 1 divided by 137. So this normally the cross-section of this process will be 2 orders of magnitude lower than during the Compton scattering. However, you have z square coefficient. So z is the electron, sorry, the nucleus charge. So for instance, I think for aluminum, for instance, it's 14, if I remember well. And so the higher is z. So this is why people use lead shields to protect from the gamma ray radiation, because that's the high z. There is a higher probability of interaction. So at some point, the z square can be compensating for the one fine structure constant. And so you can have the cross-section of the process, which is competing with the Thomson cross-section. So this can be important in a matter with high Z. So to detect gamma rays with this energy above 10 MeV, so the materials, you need a material with high atomic number to be able to ensure that you will catch the gamma rays efficiently and they will not leak through matter. So this underlies this detection technique, which is used by Fermi Gamma Ray Space Telescope. So this is an instrument which is, so this is a space observatory, not ground-based. So this is orbiting in space and contains 2 instruments. So the Large Area Telescope, or LAT, which is a pair conversion instrument. So it's high Z material catching gamma rays. And there is another instrument, which is Gamma Ray Burst Monitor. So it detects gamma rays with lower energies, and well, it's using it's trying to catch the gamma rays and efficiently sending alerts for the gamma ray bursts. So we will be focusing in this class on LAT. So this is instrument operating. So yeah, this is how the LAT looks like before it was sent to space. So this is the shield. So this is the detailed structure. So the LAT was launched, the Fermi LAT was launched in 2008, and it's operating 12 years, 13. And it is composed of a tracker. The main part of the instrument is tracker. So it's made of layers of material with high Z to favor the larger cross-section of interaction, so that more gamma rays will be producing pairs in the material. So we have this sort of sandwich called the tracker and anti-coincidence detector, which ensures it actually rejects the cosmic ray background. So these are charged protons, which also they represent the background, since we want to measure only gamma rays. So we will be rejecting the cosmic rays with anti-coincidence shield. And then at the bottom, there is calorimeter, which is measuring the energies. So how is it working? So a gamma ray, which enters the detector, it experiences the conversion in electron-positron pair here. And so the higher is the energy of the gamma ray, the lower will be the angle between those two. So when the gamma ray energy is much higher than the electron rest energy, which is 511 keV. So you will be having, again, writing down the momentum conservation law and energy conservation law, you will find out that the angle between electron and positron, which are going aside, will be decreasing with the energy of gamma rays. So the kinematics rules, and you will, for a higher energy gamma rays, you will have lower and lower angle, which is more or less scaling with so the angle will be more or less twice the electron energy divided by energy of gamma ray in radian. And so the particle shower will be going directly through these layers, and these layers are equipped with tracking detectors. So each time a particle, the electron positron, they hit the layer, there will be electronics triggered, and they will be readout, and it will be, so you can track each time it traverses the layer, the trigger is working, and so you can track where exactly in the detector particles are, so you can trace the trajectories and reconstruct the trajectories, so the angle and the detailed shower development. So this allows you to, knowing these trajectories, it allows you to reconstruct from where the gamma ray arrived. So it can arrive inclined, right? It can arrive straight, or so you can reconstruct the angle. This angle and the arrival direction from where on the sky the gamma ray arrived. So you can know the arrival direction, and then these electron and positron, they're arriving at the bottom to the calorimeter, and this is where their energies are measured. So the electron and positron, so there's the sum of their energies roughly is equal to energy of gamma ray. Okay, not exactly, but very close to that value, because electron and positron, since they're charged particles, they're losing their energy via ionization losses. So they're ionizing atoms on the way. But this process, okay, the amount of energy they lose on their way is very small compared to the initial energy typically. So you can reconstruct, so there are shower simulations to reconstruct it more precisely, but roughly the sum of their energies corresponds to the gamma ray energy. So, and this is expressed with this formula. So now you know the arrival direction of the gamma ray, you know the energy, and so observing certain source and accumulating many gamma rays, you can tell something about what's going on in the source. So you can construct a distribution of the photons in space. So more or less, you can compute the gamma ray image of the source. Okay, for point source, probably is not as exciting, but for a gamma ray extended source, for instance, Large Magellanic Cloud or Crab Nebula, is more interesting because you can see the structures. You can tell something about what are the physical processes in the source based on the structure, and then you can compute the spectra just by binning the photons in energy. So you will see, this will tell you what physical processes are operating. And so very briefly about the LAT specifications. So it's operating in the range 30 MeV to 1 TeV. So why 30 MeV and not 10 MeV, you may ask, because the pair conversion technique is working above 10 MeV more or less, but the trick is that there is a lot of noise and background in the range from, let's say, 10 to 30 or even 50 MeV. So in the reconstruction of the shower, these trajectories is very imprecise. So you got large error bars. So in practice, 30 MeV is where you start to see the, well, when you start to reconstruct more precisely. And why 1 TV? So ideally, I mean, this technique can work up to infinity, but in practice, you need large collection areas. So you need a detector. Well, the typical spectra of sources are that they are power low with decreasing, well, the flux of photons from the source is dropping with energy. So it's very difficult to produce very energetic gamma rays. And more energy, the more difficult it is to do for the processes operating there. So it's about, it has to do with the inefficient acceleration of particles up to after certain energy. And so the photon rate is dropping with energy, and you've got very few photons per square meter per second. And typical, for instance, Crab nebula, you will need to have something like 10 to 4 square meters collecting areas in order to detect only a few photons per month. And well, it's very difficult to launch something that big in space. And yeah, so after the energy of more or less 100 GeV or 1 TeV, another technique is used. So the ground-based Cherenkov telescopes. So, and below that energy, so the pair conversion technique. So the effective area of the LAT is around, it's a cube with the surface of 1 meter by 1 meter roughly. So it's 10 to 4.
Sir,
Sorry?
sorry to interrupt, but somebody's asking if you could please check the chat.
Yes. Yes, sorry. Sorry, I didn't notice the, all right. So what about telescope at space? Space telescope is the same thing, photoelectric effect like an Einstein formula. And another one, what are the difficulties for a point source? Can we improve those sources, or they ain't nothing we can do in this modern day technology? Okay, so for the first question, I don't think I understand. What are, yeah, so LAT is a space telescope, but it's using per conversion technique. Photoelectric effect is used for lower energies. It's used for more for, sorry, for let's say for energies below 100 keV, which is very hard X-rays. So yes, so you cannot use photoelectric effects to detect those gamma rays because the cross section is very negligible and it's dropping as E-3, so you can't use it. Is that the question? Like, did I answer the question, or because I don't think I fully understand? Oh, sorry. Yes. Okay, so, and for the next question, so difficulties for a point source. Yes, I mean, I was talking about constructing images. So for point source, it will be simply just, well, not exactly a point, but depending on the point spread function, it will be just like a core with a halo. And so this is used, you need images anyway, you need to collect photons in which are contained in the point spread function. So you need to see if there are other sources. So, but yeah, so, but analysis is somewhat different for point source and for extended. So yeah, so there are no difficulties with point sources. It's more easy to analyze point sources, in fact, than extended ones. So I hope this answers questions, because I don't know. Did I answer? Or if you have another questions, please, yeah, put them in chat. I will look it up. And so I have it in front of my face. Okay, I think we can continue, and if you have more questions, I will monitor the chat. And so, yeah, so effective area, it depends. In fact, it's geometric area is, yeah, it's 1 meter by 1 meter. So it's 10,000 square centimeters, which is, well, it's a decent for detection up to 100 GV or 1 TeV, depending on the flux. But it depends heavily on the energy, in fact. So the effective area, so it's the more or less the surface which is catching the gamma rays, if you can say that. So it is really dependent on the energy. And yeah, so the effective area depending on energy is contained in the IRFs, instrument response functions, and we will talk later. So the field of view for the LAT, so this is a very big virtue. The advantage of this instrument is that it's a wide field of view instrument. So it has 2.4 steradian, which is 20% of the entire sky, not even the half sphere, but of the entire sky. So it can see many sources at once, contrary to say gamma ray to Cherenkov telescopes, which see only 5 degrees field of view, or yeah, something around that value, so very narrow. So you can monitor many sources at once, and it is like the observational strategy is different. So you can be sure almost every time that you will have the data of your source, because it's monitoring a big portion of sky. And the precision for the source location determination is very good, around 1 arc minute or even half arc minute. But don't confuse it with the angular resolution, which is a bit different thing. So this is not angular resolution, but this is how well we can, it is not about separation of two sources from each other, but it's more about precision of source location. So how well we can determine from where our gamma rays are coming. All right, so for the next, sorry, yes, so the gamma ray, I was talking about binning gamma rays in space, so the arrival direction. So if we take the gamma rays of 5 years of observation of Fermi LAT, so it was in 2013 more or less, so all the gamma rays detected about 1 GV, all the, let's say, gamma rays which are well reconstructed. Again, I will talk later. So the 5 years of gamma ray data and about 1 GV, and bin that in space. So we know arrival direction for all of them. So this will be the view of the gamma ray sky. So you can see so this is the entire sky in gamma rays about 1 GV, based on the accumulated 5 years of Fermi LAT data from 2008 to 2013. So you can see a lot of point sources here. So some noise background, many point sources, which are mostly blazars. So these are AGN with the jet, which is pointing right to your face. So to the direction of the observer towards the Earth. And you can see that so this is the galactic plane, and it's shining in gamma rays. So what's happening in the galactic plane? Why so many gamma rays are coming? What is the source? So the source is that, so we've got so the most abundant material in the interstellar medium. So yeah, so you see this is the view of our galaxy more or less. So the most abundant material is just hydrogen, which is 1 proton and 1 electron. And so you know that the universe is, so the universe is full of cosmic rays. So they are arriving more or less isotropically from all the directions. So one is a lot of cosmic rays, they enter the interstellar medium. So these are charged protons, heavy, not heavy, but very energetic protons, which are hitting the protons in the hydrogen of the, so interstellar medium hydrogen. So there is a reaction, so proton-proton interaction. So cosmic ray proton is colliding with the interstellar medium protons. And when two protons collide, so this is basically what they're doing in the LHC, Large Hadron Collider in CERN. They're colliding protons and they're exploring what are the fragments. So this is happening all the time in our galaxy. Every second we have these interactions. And so during these interactions, the most probable outcome is that there will be charged and neutral pions arising during this introduction, so p mesons. And so the pi zeros, one of the variants of the products, are the pi zeros. So these are particles which are composed of quark and antiquark. And so when charged pions are born, so they live, they live very shortly because the electromagnetic processes are involved. So it's around 10 to minus 13 seconds. I don't remember, but their life is much shorter than the charged pions. So these pi zeros, they're immediately decaying into gamma rays, 2 gamma rays. And so, what you see in the galactic plane are these gamma rays arising from the pion decay when cosmic rays interact with the interstellar medium. This is why the galactic plane is shining. And so this represents heavy background for our observations. So it is very difficult to observe anything in the galactic plane, but okay, there are now good templates of these interactions, so we can subtract this surprisingly well, this background, and have a rather clean observations of whatever we are observing in these. For instance, Crab Nebula is somewhere in this plane because it's in our galaxy. So it's a supernova remnant. And so we have to subtract it very well to obtain information about the sources which are located in the plane, which is also the case for point sources located near the galactic plane, by the way. So now I'm going to talk about Fermi LAT data analysis. And so in the slides I sent you, so these boxes, they're actually clickable and you can click and get so it's a link, there are links, and some of them, there are these links which I sent you already, but okay. So the Fermi LAT data, so it's publicly available. Everybody can access it and download the tools for analysis. Everybody can perform the analysis. And so we can try to do that on Tuesday. So the data is available via the Fermi support website. So if you want to check it out, click here. And then there are 2 types of data products. So data files are either in the form of event files, which contain information about the photons of the gamma rays, so reconstructed arrival direction and reconstructed energy for each gamma ray which was detected. And the spacecraft file, so this is the let's say it's the diary of the Fermi LAT. So it's information on where the spacecraft was located, where it was pointing, so orientation, position of the spacecraft located, which is binned in 30-second intervals. So it's a very heavy file. It is very, well, the file size is very large, so and the processing times can be long, but we need this information for, I will talk about it later. So there are 2 ways how we can analyze the Fermi LAT data. So 2 techniques. So one technique is yes, okay. I see in the chat someone asked me so about inverse Compton scattering. So okay, I will first reply to this. So about inverse Compton scattering, so well, inverse Compton scattering is inverse of the Compton scattering is, so in Compton scattering is when the photon is transferring energy to electron. So the electron is gaining energy and the photon is losing energy. So inverse Compton scattering is reverse when the electron is high energy electron is transferring energy to low energy photon, and the photon is gaining energy. So there are two different settings. Yeah, so Compton scattering occurs typically, yeah, X-ray or gamma ray hitting a low energy electron, and then the photon is losing part of its energy, and the electron becomes more energetic. So this happens in a variety of sources where there are proper conditions for that. And the inverse Compton scattering is happening, for instance, in AGN jets, in blazars, and yeah, even in supernova remnants. So the inverse Compton scattering is when you have a lot of high energy electrons with energies, I don't know, GeV or more TeV. For instance, in jets or in supernova remnants, you can have TeV electrons. So these are electrons accelerated via shock acceleration or Fermi 2. And then you have photon background. For instance, cosmic ray, CMB, the cosmic microwave background, which is, well, microwave, or you can have synchrotron radiation or another low energy target photons. So these low energy photons are interacting with high energy electrons, and so the electron is losing energy and the photon is gaining energy, and it's scattered to X-ray or gamma ray. So for instance, the many spectra, for instance, spectra of supernova remnants or blazars, they have two bumps. So first bump is the synchrotron emission. So when the electrons are gyrating in magnetic field, and then these photons are upscattered by the same electrons, and you have high energy component in gamma rays. So a significant fraction of gamma rays in the energy are in fact produced via inverse Compton scattering. So this is one of the mechanisms how to produce gamma rays. So, yeah, gamma rays, when talking about interaction with matter, so gamma rays interact with matter via simple Compton scattering because it's more energetically favorable for gamma ray interacting with low energy to lose energy rather than gain. So the inverse Compton scattering will happen with low energy photons like infrared or optical, which are hitting high energy electrons. So we can continue next with Fermi LAT data analysis. So we have two, sorry, yes, I think I did notice one more question. So with this advantage, why we are building the CTA rather than focus on the space telescope? Yes, so for the wide field of view, right? You meant, so why we're building. So yeah, in fact, CTA will comprise different telescopes. So low energy part will be covered by large telescopes, and these instruments, I mean, the advantage of those low energy, for this large telescopes to Fermi LAT, they will have higher sensitivity and higher collection areas. And so these two advantages seem to be more important than the wide field of view, which was sacrificed. And another issue is that obviously launching larger instruments in space is very costly, and it's cheaper to build. Although CTA is very expensive, it will be much more expensive to construct. So to reach the effective areas and sensitivity provided by CTA at energies around several tens of GeV, we need really, I mean, at least 10 meter by 10 meter instrument. And this is very, and okay, I think this is very costly. And let's say the strategy, I mean, Fermi LAT will continue operating, and so its data will complement the data of CTA. And okay, so the observational strategy can be modified depending on the behavior of the sources. So for instance, if there is interesting behavior like flaring, so if the source is showing increase of flux, it's interesting to understand what's causing that, what are the violent processes. So typically Fermi LAT, which is observing with very wide field of view, which can see many sources, the program, okay, there is an alert software, so it's sending alerts to other instruments, and if there is a source which is showing interesting behavior, one can, so the alert is issued, and the let's say for the moment, for instance, has telescopes can be triggered and follow up the specific source. So there is a very different strategy for observing. So Fermi LAT is more, works in this range more like alert issuing, and we can do the same with CTA. So CTA can monitor the specific source only when needed, when there is an interesting behavior. But also it's worth to note that in higher energy range, so around 10 TeV, about 1 TeV, so in the range where CTA small telescopes will be operating. So there is another instrument, so HAWK, high altitude of, yeah, what's the acronym? Sorry, so high altitude water Cherenkov telescopes, yes. So these are water tanks placed all over the desert, all over a portion of a desert in Mexico at high altitudes. And so they're detecting gamma rays. So the same technique. So the gamma rays are hitting they're converted. So they create showers, the same showers as in atmosphere, but water is more dense. So you have smaller shower extent. So so HAWK is having a larger field of view. So it has very similar field of view to what Fermi LAT has. So HAWK this instrument, it has very wide field of view for energy range of 1 TeV or above that, but it has very poor spectral reconstruction. So let's say it is very challenging to produce high quality detailed spectra with HAWK. So, and timing resolution is not so good. So in this regard, so Fermi LAT and HAWK at higher energies, they will be complementing well the CTA. So, and these three instruments are going to work in synergy. So HAWK is very good at angular resolution, at wide field of view, and CTA is very good for point source, for specific sources. So these three instruments will complement each other perfectly, or almost perfectly. So yeah, this is why there is this strategy to build CTA. So hope this answers the question. So next, so yes, the Fermi LAT analysis, yes. So you can have two techniques. So first is aperture photometry or likelihood analysis. So aperture photometry is in fact very straightforward. So you just count the photons. So if you have an experience with optical data, so you just count the number of photons in pixels and you have the flux. So it's very easy, but it has many drawbacks. So the analysis is anyway, whatever you do is performed using the Fermi tools package. So this is the dedicated package developed by Fermi collaboration, and the software is updated regularly. So the one who is involved in the analysis has to make sure to update. So for the aperture photometry, so what are the advantages? So it's quick, and it provides model independent flux measurement as you're just counting photons, nothing more. It's less computationally demanding, and you don't involve any heavy mathematics in there, and you can use shorter time bins, so you can have very precise light curves, very detailed light curves. But it has two very, very severe drawbacks. So first is it's providing very rough background modeling because you're relying on counting photons only. So you're not developing any models of background. You're simply counting background photons. And if you have very poor statistics, you have very imprecise background measurements. For instance, you counted 5 photon backgrounds in your circle, but you know, the smaller amount of photons, the higher is its Poisson statistics. So square root of 5, 2.7 or something like that. So you have very large errors on the background. It's very unreliable. And so yes, and so you have, due to this very important drawback, you have a very inaccurate flux measurement compared to likelihood analysis. So it's more or less like quick and dirty approach, which is very good for a quick look. For instance, you need to send an alert, you need to compute the flux, you have to show that this flux is higher than a certain threshold, so then the average. So it's very good for quick results when you need to evaluate what's the behavior of your source very quickly. But for a reliable analysis, for publication results, for making some conclusions about the source, you need really to involve likelihood analysis, which is a whole different story. So it can be in 2 different variations. So you can have binned likelihood or unbinned likelihood. I don't want to go really into details, but the important message to say about those differences is that binned is suitable for very good statistics when you have lots of photons and you want very precise results. And unbinned likelihood is suitable for very poor when you have short observational times or very faint source. So unbinned likelihood analysis, okay, there are different methods involved. So to work with the lower statistics in order to have still accurate results acceptable for a publication quality. So in likelihood analysis, you have thorough background modeling, because so how is this done? So you have, again, I will explain later what is the background, but all the background is, there are specific physical models of the background. So how the background is arising, and there are templates for background, and you can model background very precisely. So a couple of slides away. So this background, as you see here, is in fact very well, like it's modeled via dedicated templates. So you can have a detailed source modeling. So why? Because you can specify the model of the source. So for instance, if it's an extended source, so you can specify detailed spatial template, or you can specify the spectral model like a power law or a log parabola. You can have, yeah, you have a whole bunch of instruments to work with to model your background and source. And also, due to these virtues, it has, so you can reach much higher sensitivity. So you can detect faint sources more easily and more accurate results. So, and it provides more accurate flux measurement. So you can measure the spectra and light curves, so the flux variations very precisely, and make conclusions about the behavior. So, but there are also disadvantages as every time. So it's less computationally, let's say it's less quick. So you need more resources of computer. You need more time to compute the spectra. You need more, and you have more analysis steps involved. So you need to spend really more of your time to have the results. And okay, it has to be, you have to be cautious, because the flux determination in this case is depending on the models you're using. So you're reconstructing, it's more like you're guessing although it seems contradictory and it's ironic that it allows to reach more accurate flux, but you have to be really sure about your models, because if you're specifying wrong models, then you can have totally different flux. Okay, the whole analysis chain. Okay, it's the way the analysis is organized. Even you have complete stupid model, let's say not really something unrealistic, but if the model is not very accurate, if it's way too simple, you will still get very accurate results, but you have to aim to have much better models to have very accurate flux measurement, but you have to be aware that it's model dependent. But overall, so this method is preferred for data analysis because it's like more rigorous approach. So I have a question in chat. So it means with this method, the light curves can be computationally used to analyze, e.g. we can check the Compton dominance from light curves. Yes, so the light curves, yes, so you need spectra and light curves to understand what's going on with physical processes are in the source. So yes, you need to perform modeling of the data, so you can usually you have certain physical model of your source, and yeah, if you suspect certain processes, so you include them in the model and you can try to reproduce the data. So after you do the analysis, all the analysis steps, you have light curves and you have spectra, and the next step is to interpret them. So this is where the job of astrophysicist starts really. So before it was more like detector analysis, particle physics if you want, and then the interpretation. So you can do the primary interpretation. Some spectral features may indicate you various processes, or mainly this spectral shape or the light curve shape. So if you have flux rise or anything, yeah, usually there are only two features in the light curve. So it's either flux increase or decrease, I don't know. So you can collect all that information and try to reproduce it with the model, and improving your model by adapting it like to fitting the data. You can really make conclusions about the processes. Okay, so next is, okay, I'm gonna make a detailed, yeah, I'm gonna present in more detailed way each of those two methods. So for aperture photometry, so what you do, you just extract the gamma ray photons from a circular region around your source and bin them in energy or time. So this works the best, obviously, with point sources. So for extended sources, it's less good, and you can imagine why, because you don't know how to exactly draw a region where the source is ending, because you don't have a strict boundary. So here you have more strict boundary where you see that the source, okay, you have much less photons. So the point source, but you see that the photons are actually, you don't have one single point or whatever. So you have some extent. So why so? Because you have point spread function. So the photons are smeared over a certain angular extent. And this is due to the instrument response. So you need to collect photons from more or less the entire point spread function. So you select a region, certain region around the source. So this is the source region, green. And then you need to, well, it's polluted with the gamma ray background. So you need to extract gamma ray background from the vicinity of the source. So you select several source-free regions. So for instance, 4 regions around the source. So why 4? Because you need to make the background measurement as more accurate as you could. And for that, you need several regions to make an average, so it will be more precise. And the larger the region is, the better. So the better averaging, and you select, for instance, the radius of this region, in this case, is 2 times larger. So you have 4 times the area of the source region. And then next, so the aperture photometry method is described. So you click here and you can see the manual on this on this method. So you choose a circular region around the source, choose background regions, then select the data from the source region and from the background region using Fermi tools. In the Fermi tools, you've got sub-tools which are working, so they're making dedicated procedures. And they start with GT, and then the next part of the name is what the tool is doing. So GT select is what the tool, so the tool is used for selection of photons. So you can apply different cuts. You can apply, well, you select on the basis of the information you want to get. So for instance, you select, in this case, you select events only from source region. So you specify the location of it, so the center, the radius, the same for the background region. So then you ensure you select only from a circle. Then you can select the time range. So you want energy, so you want photons from only a specific time range, from this day to that day, or a set of time ranges. Then you want probably to also cut on energy range. So you want, for instance, about 1 GeV. So from 1 GeV to the highest energies, and then you select the source, the photons which are having the high probability of being photons. So as I said, the reconstruction, okay, in some cases the reconstruction can be challenging, can be difficult. So and during the reconstruction, so each event is assigned a class, so event class, and for the events which were well reconstructed and the conditions during observations were good, so they're assigned specific class, event class 128. This is something within the tools. So if we are going to do that next Tuesday, so yeah, I can show the scripts. So you have to specify as an input for these tools, so event class 128. So this is the high probability of being gamma rays, because sometimes the particles can be also misclassified. So despite the shield, the anti-coincidence shield, the cosmic rays still can penetrate into the detector and being classified as gamma rays, because they can also induce showers and well, there is no, let's say, you can confuse the gamma rays with cosmic rays. Misclassified events are assigned a different, okay, each time you reconstruct an event, there is a kind of event quality, so probability of being a gamma ray. So the events which are misclassified, they have lower probability of being gamma rays, because the shape of the shower, how is it measured? Because there is a different shape of the shower when, well, for charged particle and for gamma ray. So if there, and there is no really clear transition so between them. So depending on the shape of the shower, this probability is calculated. So if you suspect that the events are probably misclassified, then you reject them. So, and you said if you have poor statistics, you can select all the events to have an idea, yeah, at least to have some light curves. But if you have enough photons, you have to really do cut on events which are probably gamma rays. Then you need to cut on the event type. So basically so you have different conversion types. So front conversion, back conversion, because photon arrive from, well, from different directions, and if you observe, well, you can observe, it's not only that, well, if you're observing during a narrow time interval, then your source is more or less the same position. But if you accumulate large amount of data, then you really need to cut on the event type. So there are three subtypes of the like the event, yeah, three subtypes. So depending on the conversion type, depending on the PSF, so which PSF type, because the PSF depends on the energy. At low energy, the point spread function is much higher, much greater, and so you've got much poorer angular resolution and energy reconstruction, so the way the energy was reconstructed. So typically you don't have to think too much about that because there is a standard value which is selected, and if you want to do more sophisticated analysis, then you can start digging into that. But for simple applications, you just specify one standard value and you don't really care more. And you need also to cut on the zenith angle, so to remove the earth limb background, because it's background gamma, it's source of background gamma rays. Next, when you have selected all the events from these regions, from regions in certain time range, energy range, and so on, and you have selected good events, you have to select intervals where you had good data quality. So the good, so-called good time intervals. So good time interval is something, these are intervals when when LAT was operating properly and when it was outside of some perturbing areas, or when the data taking was in standard mode, because the instrument can be perturbed by by different, it can be affected by different things, but mainly you need to select those intervals when the instrument was working properly, and so then the cut is applied, and so you have only events from those good time intervals. Then is all simple. All you need to do, if you want to produce images, you need to bin the photons in space. So you select like a grid of pixels and then you bin them in space, and you have your image. To get the spectrum, you bin the photons in energy. So you have energy bins and you distribute them among the energy bins. And then if you want light curve, you bin your photons in time. So you have your wide energy range and you bin photons in time. So yes, and then if you want, all this is done by a tool named GTBin. So GT is the starting prefix and bin is because it's doing binning. So what do you need to indicate to the tool? You need to indicate which algorithm you want, so spectrum or light curve or map. And then width, you want to specify the time bin, so width of the time bin or energy bin. So it has to be narrow enough to have detailed spectrum or light curve, but wide enough so that you have enough photons in there. So you want for spectrum or for light curve at least 30, 50 photons for good quality. Otherwise, the light curve will be very unreliable. So you adapt your binning to the statistics. Then you calculate the exposure. So exposure is something specific to this, let's say to gamma ray instruments. So it's a quantity which depends on the response. So it's a characteristic of the instrument response. And it is depending on the effective area and it's depending on the observational time. So it is measured in centimeters square by second. So in order to get your flux, you need to divide the number of counts by exposure. So, and you will have, so this is, let's say, effective area multiplied by the effective observational time, but convolved with the IRFs. So you need to calculate exposure to get the physical flux. So to calculate this exposure, you need to know, of course, the observational time, and you need to specify the IRFs, the instrument response functions you want to use. And since these are also, these are updating, so say 5 years ago, there was much poorer energy reconstruction at low energies. Now it's somewhat better. So you need to specify the functions you want to use. I can show that next Tuesday. And also, okay, what are the IRFs? Okay, this is instrument response. So this includes point spread function, PSF, the effective area depending on energy. Okay, all of that heavily depends on energy, and energy resolution. So spectral index is also affecting your well, the exposure calculation, because it needs to assume certain source model to calculate the, because you have dependence on the energy. So in order to interpolate that, so you have to guess, provide a good guess about the spectral index of the source during that time interval. So if you don't know, you specify, for instance, -2, and then when you get your spectrum, if you see it's very different, you can rerun analysis with a different one, so it can be iterationally improved. It's okay. And so finally, okay, what you have your number of photons in each beam, you have your exposure, and then you simply divide the number of photons by exposure, and you've got your flux. So to calculate flux, you need to divide number of source counts. So these are counts from here, and background counts are from here. So number of source counts minus average number of background counts, normalized. So if you have twice the area here, you have to divide, sorry, 4 times the area, you have to divide by 4. So averaged over 4 regions and normalized to the source region. So divide by 16 in our case. So by 4 because 4 regions, and divide by 16 by 4 because we have twice, 4 times the area. And so this gives you the number of pure source counts, and dividing by exposure, you have the physical flux in photons per centimeter square per second. And so exposure takes into account the PSF, because number of counts is not exactly the number of photons. The number of counts can be lower because you don't really catch it. The number of counts you detect depends on the response of your detector. If you have 10 photons, it can, for instance, trigger only 5 counts or 2 counts. It depends on the observation. Like the response depends on energy, so you need to take that into account. So exposure is taking into account the response of the detector depending on energy. So when you divide number of counts by exposure, so it compensates. So you have, at the end, you have it converts it into photons and per centimeter square per second. So you have physical flux. And how to compute the error? Okay, this is Poisson statistics. It will be assuming Poisson statistics. So if you subtract 2 quantities, so the error on their difference will be the square root of the squares of the quantities, right? So the square root of the squares of the, so you have well, the square root of the squares of the errors. So the error is square root of these quantities. So square of square root is just these quantities. So the total error will be number of source counts plus number of background counts, all square root divided by exposure. So this can lead to satisfactory, but let's say quite not very accurate results. So aperture photometry is good for quick look if you want to quickly estimate the flux of the source. So now about the likelihood, so which is a more rigorous and precise approach. So okay, this is a whole different story. So for likelihood analysis, yes. So for likelihood analysis, you reconstruct the source flux in a way, so depending on the model. So you reconstruct the flux from the source using maximum likelihood optimization technique. So we need to, we deduce the flux which would yield the highest probability of the data that we measure. Let's say, I will explain it now. So what do? So we need to assume a certain model of our source. So if it's an extended source, we assume, so its shape, then we assume it's spectral. So how the flux is distributed over the energy. So it's a power law with a specific slope, or it's a something more or less if the spectrum has curvature. So we use our best guess and we set the model, and this is our hypothesis. So we assume that the source model is, okay, some given model, and it has set of parameters, for instance, normalization. So what is the flux at 1 TV or at 1 GV? And then we also the spectral slope. So how tilted is the spectrum? Or if it has curvature, what is the curvature measure? So, and these parameters can be varied. So we need to find the parameters for which we have the most highest probability to obtain the data we observe under the assumed model. And for that, we use likelihood approach. So what is exactly likelihood? So it's a mathematical concept. So it's not exactly probability, but it's proportional to probability. So we can say likelihood is a measure of likeliness that, well, you like the model with a specific set of parameters would yield you the observed data. So you have some model. So for instance, probably if you flip a coin, right? You know, for instance, the coin is fair. So center of mass, everything is perfect. You know, it's 50% heads and 50% tails. And so your probability is, well, you predict how probable will be heads or tails. Or if you know the coin is unfair, if you have 60% heads, so you just predict what are the chances of getting a specific measurement. Here you have reverse. You have a set of measurements. For instance, you flip a coin and you have, I don't know, you have these number of tails, these number of heads, and you, for instance, you get 60% times heads and 40% tails, and the total number of measurements, I don't know, you were flipping the coin 10 times. And so you want to know, so your hypothesis is that the coin is fair, or your hypothesis is that the coin is, I don't know, 60% more shifted towards heads. You assume something about the coin, and then you check based on the data, your hypothesis, so you calculate the likelihood, and the likelihood will tell you how likely is your hypothesis of the coin being fair or being unfair with a specific parameter, given the observations of how we were flipping the coin. For instance, if we were flipping 10 times and we've got 60% tails, then okay, we can still hope that the coin is fair. But okay, it's not sure already because the likelihood for 60% will be higher. But if we were flipping the coin 1,000 times and we've got 60% heads, then the highest likelihood will be picking near, the likelihood of a coin will be fair, will be very low. The highest likelihood will be that the coin is actually not fair, and the fairness parameter, or let's say probability of heads, is around somewhere in the vicinity of 60%. So I hope you got the concept of likelihood. So it's when we try to evaluate how likely is our hypothesis given specific data. So the more or less measure of the likeliness of hypothesis, which we assume that the observed data can be raised from a specific model with specific parameters. So the mathematical formulation is that there is a prior probability, is what we assume. Okay, the coin is fair or whatever. And then there is a posterior probability. So it's the probability of having this parameter. The coin is fair, 50%, let's say the prior probability of getting heads, 50%. We assume coin is fair, but posterior probability is the probability of the, so you see prior is a probability distribution of the parameter, and posterior is the probability of the parameters given the data. So probability of fairness of the coin, for instance, given our measurements. So the likelihood is the posterior divided by prior. So it is proportional to the probability of data that we got given specific parameters. So, and this can be used to iteratively improve our guess about, for instance, fairness of the coin. We assume prior is 0.5. And then we measure we flip the coin and we measure the likelihood. and then we see, okay, the posterior probability of the coin is fair is very low. For instance, we made 1,000 measurements, and so we improve our guess about what is the probability of heads based on the data. So we use likelihood in order to evaluate the likeliness of the hypothesis. So it's not exactly probability, because for instance, it doesn't obey the law of integrating or summing up to 1. So the sum of probabilities over a specific range will be equal to 1. But for likelihood, this, for instance, doesn't hold. So you won't have sum of 1, and it's only proportional to probability. So it's, as I said, it's proportional to probability of the measured data given our parameters of the model. So again, what's the important difference between the notion of likelihood and probability, right? So probability is only quantifying a chance of particular situation to happen, and the probabilities, they attach to possible outcomes, possible results for the same hypothesis which is regarded to be given. So likelihood, it's actually the reverse of the probability in some sense. So it's quantifying, it's inverse, so it's quantifying the likeliness of a specific hypothesis when we already have the data. So it attaches to various hypotheses we can assume for the same given set of outcomes, for the same given set of measurements and results. So, and let's say the likelihood function, it has no real specific meaning. I mean, you cannot really interpret it, the value of it. Like if you see the value of if you compute likelihood function and the number you get, it doesn't tell you anything contrary to probability. So if you have probability of rain tomorrow 20%, you more or less kind of, you can sense it somehow, but the likelihood, the value doesn't give you anything. So all what means is the different values for different hypotheses. So you use likelihood ratio, for instance, to find what hypothesis is more likely given the same data. So you compare different hypotheses, the most likely hypothesis with highest likelihood value. So only the ratio of likelihood means something. And so coming back to the likelihood analysis used for Fermi. So as I said, we assume certain model for the source with first guess parameters, and then we optimize the function. So we fit we vary the parameters and find that parameters which maximize the likelihood function so that we have, assuming a certain model of the source, the data that we observe appears to be the most probable. So for instance, this plot shows the example. So we assumed a certain, so for instance, a power law for the shape of the spectrum, and we assumed a certain scale that our flux from the source about 1 GeV will be, let's say, 10 to minus 7 photons per centimeter square, with a certain prefactor, which can be from 1 to 10. And we know more or less the range where the source flux should be located based on previous data, for instance, but we don't know exactly, we know order of magnitude, but we don't know exactly the prefactor. So we have our observational data and we have our model, and we iterate through prefactors and see which one maximizes the likelihood function. So here the likelihood function has the highest value around 4.2. So we can say our flux from the source will be related to this value. So step 3, flux from the source is directly related to the inferred parameters from the likelihood optimization. So the scale which we guessed, like for instance 10 to minus 7, so the flux will be 4.2 multiplied by the model scale 10 to minus 7, for instance. And then we know the source flux, and so we get so we do it repetitively in different energy bins, and so we get our measurement for different time intervals or different bins. And as you can see, so the resulting flux is very depending on the model which we assume. So if we assume a very different source model, we can have somewhat different results. So now you may be curious, how do I measure the error bars in this case, the error? So I have my value of the parameter, and from where do I get how can I be sure about this value? Like, this is also likely, but less likely. So where is this transition? What is the threshold? In fact, so to infer the errors, you use so the likelihood. So there is a theorem that for high number of degrees of freedom, your likelihood function scales as, I think, E minus chi-square. I don't know if you know about least square optimization or chi-square. So they kind of minimal chi-square is, okay, it's intertwining with the concept of likelihood. But okay, there is a rule that for 1 degree of freedom, for instance, you have the likelihood. So yeah, I forgot to mention, so here I plot the logarithm of likelihood function. This is usually the quantity, so maximum, so log is a monotonous function, so you want to plot log because it can have very different, well, smoother representation because it can be spanning many decades. So the rule is that the logarithm, the natural logarithm of the likelihood function, has to drop by 1/2 in order to get the. So if your likelihood function, so the ratio of likelihood, you see, so you have E, so likelihood ratio. You have the log so natural logarithm is dropping by 1/2. So, and this is where it is regarded that the results below that are less likely, so almost not likely. So, and this will be 1 sigma errors. So here I plot actually the 10 based logarithm, so log 10, and for a log 10 it will be converting that, it will be decrease of the likelihood by 0.2. So you see, so here is the peak, it's around 2.7, and so decrease should be by 0.2, so around 2.5 if our likelihood, log likelihood, is below 2.5. So these results are below our region of confidence. So if you draw the line, it will intersect the plot twice, here and here, and this will define your errors. So you drop it here on the x-axis where this drop occurs. And so you see it will be around, I don't know, 3 or something like this. And when intersecting, I should have drawn this on the plot, but okay. So here is around 5. So you see, so your flux is around 4.2 plus minus, let's say 0.8. So it's spanning, it's located in the interval from, I don't know, from more or less 3 to 5, but with the highest probability. So you can write it down as 4.2 plus minus 0.8 or 1, I don't know. But during the real analysis, so you don't need to do that with the plot, the software is calculating that automatically. So this is it for the principle of the likelihood function. So I will check the chat. So no questions. Okay. And now, so as I said, the analysis used for analyzing Fermi LAT data, the most reliable approach is the likelihood. So because it has higher accuracy due to the possibility to precisely model the sources and the background. So now we are going to consider step-by-step analysis, and on Tuesday we can go through that, well, using real data. So, and this will be it for today. So I will quickly go through the analysis, giving the theoretical, theoretical background, and then, yeah, that will be it for today. So the step-by-step tutorial I have sent you already, if in case you need the link again, so just click here. And so to analyze the data, you need to fetch the data from the source for your source of interest. The data is publicly available, so clicking here, and then you need to specify, what do you need to specify? You need to specify the coordinates of the source you want to analyze, or if it's an extended source, the coordinates of the more or less of the center of the source, and then the extent. So you need to specify the extent of the region from where you want to get the data. For instance, you don't want to get the whole sky, or if you want to build this nice map of whole sky, you can download the whole sky. But for a source, so you typically select, I don't know, 10, 20 degree radius around the source, because the space, the Fermi LAT PSF is actually quite wide at low energies, so you need to collect photons from large region. And so coming a bit ahead, you will be modeling this entire region, not only your tiny source. Yes, this is giving you more robust results because you can model the background. You need a chunk of background to be able to properly filter the source events. So the data you need, obviously, event files and the spacecraft file for the photons themselves and about the observational conditions. So, and for the orientation of the spacecraft, and because you want also to understand how long your telescope was observing your source in total, so cumulative. This is very useful if you want to stack some data. For instance, if you're not analyzing 1 week of data, but if you're analyzing a few years of data and you want good statistics, you want averaged characteristics. Next, so you obviously need to download the latest background models. So for a likelihood analysis, you need models of background, very precisely specified. So there are two kinds of background. So, sorry, you have galactic diffuse gamma ray background. This is exactly what I was showing in the all sky map. This red bright shining region stripe. And so this is a rise, I already explained, this is arising due to interaction of cosmic ray protons and charged particles with the interstellar gas. So you have pi-0 decay, and this is polluting heavily your view mainly in the galactic plane, but also somewhat further away as well. You have to really take it into account, especially for faint sources. And then you've got isotropic gamma ray background, and you saw these were blue dots all over the sky. So it's more or less isotropic, and with the factor of a few. And then you have so it's everywhere all over the sky, and this is due to first unresolved extragalactic sources, so many faint point sources which are overlaying together and superimposing, and then also fraction of this background is due to misclassified cosmic rays, as I already was speaking about that. So these both backgrounds are very well modeled with a dedicated templates, both spectral and spatial. In the case of galactic diffuse, you have a spatial background, spatial template, and spectral one. But for the isotropic, it's isotropic, so we have only spectral template, and all the variations across the region, you can model them, so you can leave this prefactor up to a value of a few, and you can take into account for the small inhomogeneities. So you download these models, so they're also publicly available. Just click here. Then you need to make selections. So I already was explaining fraction of the, okay, likelihood analysis involves more tools than in aperture photometry. So some tools I already explained, like GT select. So I don't think I'm going to repeat. So you select only from source region, from energy time range you're interested in. So again, gamma rays with highly high probability with good reconstruction quality, and source class, which is 128. So this is the well reconstructed events when we are sure that these are gamma rays. So we cut on the event type. So there are two conversion types. So front gamma rays arriving from the front and from the back. 4 classes of PSF and 4 energy reconstruction classes. But yeah, this is just general information for most applications, simple applications. You don't really need to care, is really for most sophisticated analysis. So for event type, usually to select a standard value, and again limp background, so typically zenith angle less than, I don't know, 100 degrees. So you selected your data, your events, so you have a sub-selection from what you downloaded. You need to apply also good time intervals. You find when your spacecraft was operating in good conditions, in standard data taking mode, and the data can be considered as valid. So nothing was interfering with the observations. Electronic was working perfectly, no anomalies. So, and then these good time intervals. So these good time intervals are applied on your sub-selection. You see, so you select only the, so you select only the data from this sub-selection of your data only from these good time intervals. So all the necessary information on how the spacecraft was operating is located in the spacecraft file. So based on these good time intervals, so the event selection, which we obtained from the previous step, GT select, so it's further filtered. And so we use also these good time intervals for exposure calculations. So very quickly, so we obviously need to know how long in total we were monitoring our source, because we need to calculate the flux. We need to divide by the total observational time to get the per second rate of photons. And in order to do that, because we can have disrupted, you can see we have one interval, another interval, so we need to sum up all these small intervals, because if you cut some specific like bad events or whatever, you need to sum up all the intervals. And so these will be the all the time intervals where you're selected, where your data was selected, and the good time intervals. So all the data you have selected, we're using the previous step within the good time intervals. So all is written down to files. So all the events, so from which range you make sub-selection, and it's all written down. What are the time intervals for your selection? So you have like a whole list of time intervals for your selection, and then these are then added up, and the total exposure is computed. Then it's getting a bit more interesting. So count maps creation. So you need to verify how your data actually looks like. You want to see images, especially exciting for extended sources like Large Magellanic Cloud or Crab Nebula. So you want to see what is in your region of interest. And so yes, the data which you selected, so you specify some, as I said, you download it from a specific region, typically 10 by 10 or 20 by 20 degrees, and this is called region of interest. So this is where your source is located and where you measure your background. So, and you use GTBin tool in order to bin your photons in space this time. So in 2 coordinates, right ascension and declination, Ra and Dec. And so you use the GTBin. So next time on Tuesday, we will go through all the steps, see how it looks like. We will really do it manually. And so the parameters you need to specify, okay, the binning, the number of pixels per axis, so for X and for Y axis, the scale of your image, so how many degrees per pixel, the resolution, and okay, if you want to use 0.2 degrees per pixel, for instance, and your total region of interest is 20 degrees, then you can already readily calculate the number of pixels. So 20 degrees by 0.2, so you will have 100 by 100. If you want more pixels, you specify different image scale, but you have to be sure that you will clearly see the details, because if you have very small number of photons per pixel, then okay, you won't see any details. Well, it will be a mess and very noisy image. So, and obviously coordinates of the map center. Typically you want your source in the center, so you have to specify that. And so this is how it looks like typically in the DS9. So DS9 is the software which allows you to open the FITS files as maps, and there are many different, so we will do that on Tuesday. We will play with DS9. So this is an example of region of interest, which contains actually two sources, so 3C279 and 3C273. So those are blazars. Those are AGN with jet, which is pointing towards us. These appear as two bright spots in gamma rays. The source of gamma rays, and there are a couple of smaller, fainter point sources, and you've got your background, which has to be filtered out. So, yes, okay. So yeah, you inspect the maps to make sure everything is done properly, that you have events, because sometimes if you make a mistake in GT select, or if you specify some contradictory information, then you might just not get, for instance, you can get empty selection. You have no photons, and then you will waste the resources for nothing. So you have to make sure that you didn't apply too tight cuts, that you get enough events, and that you don't get too much noise, for instance. So this is kind of verifying that you've done proper selection. And then when we make sure that everything is good, we can proceed to computing, to next analysis steps for computing these maps for different energy ranges. So this is called counts cube. So this is just maps for different energy bins. So we select several, we apply energy binning. So for instance, we have energy range from 100 MeV to 100 GeV, and we select bins of 1 decade wide. So from 0.1 GeV to 1 GeV, from 1 to 10 GeV, and from 10 to 100 GeV, 3 bins. So we compute maps for every bin, and this is done via a dedicated tool of Fermi tools. Again, GTBin, but with the specific argument. So C cube counts cube. So it will produce you these maps for your bins. So you specify binning. You want linear binning or logarithm or even custom from a file. Obviously lowest, highest energy and number of bins. So this is example how this looks like. So this is my results for large Magellanic Cloud. So I was analyzing Fermi data of large Magellanic Cloud, and these are counts maps for 3 energy bins. So you see 0.11 GeV, 110, and 1000. And you see that these maps are drastically different. For instance, the lowest energy map, you see that, okay, it's just a mess. So why so? You have, so the background, I forgot to mention that the background, the galactic diffuse background is dominant, in fact, at energies slightly below 1 GeV. So the pion decay, so when the pion decay happens, so the most probable, the cross-section of this process is somehow the highest probability is around 77 MeV, or, okay, I'm not sure about the figure, but it's in the range of several hundreds of MeV. So most of these gamma rays coming from the galactic plane will be in the range of several hundreds of MeV. And so this image is heavily polluted by galactic diffuse, although you know that the Large Magellanic Cloud is not, I mean, it's not within our galaxy and it's not overlapping with it. So there is some angle between the plane of our galaxy and LMC. So we have still important contribution from this background even at that galactic latitudes. So that's why it's important to model this background well. And you can see that the source is very, okay, it's very smeared and blurred. This is due to the fact that LAT has very poor angular reconstruction at low energies. So the reconstruction of arrival direction is very bad due to the specificity of the instrument response at the low energy. So everything gets very complicated at low energies for LAT. So you've got poor, very wide PSFs. So you've got everything is blurred, but still you use this data as, well, this is valuable. It's, well, any information is valuable to understand your source better. So here in the medium energy bin, okay, you see there is a good compromise between the, okay, the rightmost image from 10 to 100, you see, okay, it's the number of photons here is lower. You can even see it using the scale, so 10 times lower or whatever, and then you see that the statistics is poor, so you have just insufficient number of photons for a precise image. And here you have a good compromise between the quality of the data, so number of photons, enough photons, and at the same time good instrument response. So you have a quite decent image here. So this is the, let's say these three maps comprise the Count's cube. The next step is to specify the model of your source. So this is your hypothesis about how likely, the hypothesis which you will test the likeliness of. So you will not really test the likeliness of this hypothesis itself, but more like of parameters that are in this model. So we will find the best parameters which make the most likely. So the data is the most probable. So you need to specify the model of your source, the composite source. So what is the composite source? Is everything you see in this region of interest. So this is your source itself. So I'm analyzing here a Large Magellanic Cloud, which is this bit. So this is Large Magellanic Cloud. And these are point sources, pulsars, supernova remnants, etc., which have to be included in the total model. So we create the composite model. So we add to our model the source, the Large Magellanic Cloud. For that, we include the spatial template. So it's our guess about how the gamma rays are distributed across the source. Then we add the spectral template. For instance, I'm assuming it's just a simple power law with the slope, for instance, -2. It's source of cosmic rays. So we assume something in the around -2, or we can improve that value after first analysis. And then these sources, again, we need to model these point sources. So again, we assume the simpler your model is, the less number of degree of freedom, the more you can rely on the results, because with enough parameters, with many redundant parameters, you can fit anything. So you need to have detailed model, but no excessive parameters. So you make the model first, it's as simple as you can, and then you complexify if that is needed. And so point sources, for instance, flux at 1 GeV, you need to specify flux. So this is this prefactor by scale, and then the guess about the slope, and then the background. So the background, all this blue noise here, is the sum of the galactic diffuse and the isotropic. And for that, you don't worry, because we have templates. All you need to specify is the floating kind of this floating normalization in the typically in the range of 1 to 10, because you know more or less the order of magnitude flux from the background depending on energy. But you need to have some freedom to adjust your background, because depending on the observation or depending on the location in the sky, these can vary a bit. But in general, your background is very well coded, let's say. So, and these in total, so this will be the total model of your source. And you specify the presumable parameters for all the components of the model. And if you want to vary the parameters, you have to specify free. If you don't want to vary, fix them, so you need to specify no. So this is example of the model file. So this is an XML file. So it's written in the syntaxes of HTML, more or less, I don't know. So this is my model for the LMC, with the only difference that I, in fact, to make it shorter and not confuse you, so I included only one point source. I just threw away several other point sources for the sake of simplicity. So here we have our main source, which we're interested in, which we want to learn about. So Large Magellanic Cloud, LMC, so diffuse source. So you see there are sources, source, gamma ray sources. And then here, folded in, there are parameters, the model parameters, the models and the model parameters. So it's nested in. So what do we assume about the LMC? We assume power law spectrum and the order of magnitude. So the scale of the flux, and we allow this prefactor. So what is coming in front of the scale to vary. So when we select that, okay, we want, okay, that was a mistake. So yes or no, it should be replaced with 1 or 0, but okay. The main idea, 1 is yes and 0 is no. So we want to vary. We have an idea that this is a power law spectrum, and all we want to know is to vary a little bit the normalization. So we prefactor the coefficient in front, so keeping the shape the same. So we allow this to vary. The index, so we assume, okay, -2. Okay, and we allow that to vary. No, we don't allow that to vary. And then we set the, okay, the scale, let's say the scale in front of the, so the prefactor is the flux measured at the specific energy. So this will be the energy at which we measure the scale, the measure the prefactor, the base, so the pivot energy. And so we don't vary it. So we specify a specific spectral shape and vary only the, let's say, the height of the spectrum. Then we assume, so you can see it's a complex morphology, and I was modeling it with a specific physical model where I was calculating supernova explosions and accumulating that, and calculating cosmic ray output based on that, and then computing the gamma ray production. So I computed separately certain spatial template of this source, and I was using it as a spatial, as the let's say as the geometrical configuration of the source. And so it's spatial map. So, and the normalization, okay, I mean, it's just the geometry, so we don't need to vary anything here. And this is it for the main source, the Large Magellanic Cloud. Then there was a point source. So for point source, we go as simple as we can. We have a power law, and just in case you, yeah, just, you know, just general information. So power law in the high energy astrophysics. So this is the most simple kind of spectrum, and typically this is the most probable spectral shape you can expect, because this is how well, in most astrophysical processes in high energies, your spectrum will be more power law rather than thermal. So this comes from, for instance, particle acceleration processes. So your particles, when for instance there is a shock acceleration or Fermi 2 turbulent acceleration, have more likely power law shape or broken power law, or if you have important, let's say if you have important turbulence contribution, sometimes you can get curved spectra. But okay, this is something more complicated, and it has in fact 3 parameters. It has 1 more parameter than power law. So you want to assume more simple model, and if you see that it doesn't fit well, you add parameters, and this only if this is justified. So, but for this application, for many sources, you use the simplest shapes you can. Okay. So then, you model the source with power law, and you specify, okay, the normalization and the shape. The slope -2 again is the most common. And then, okay, there is no special extent, it's just a point source. Then you specify 2 templates for your background. So special, the background having spatial structure. So you load a template, which you download from the Fermi website, and you load to vary the normalization of it in range 1 to 10, because we're more or less sure about the order of magnitude contribution. The same for isotropic background. You download a specific file containing its spectrum, and we allow the normalization to vary, so to adjust for possible variations. And that's it. So this is our composite. So this is expression of our composite model for our source, Large Magellanic Cloud, for instance, plus other sources in the vicinity. And so with this model, we try to reproduce the observed data, or more precisely, we compute the likeliness of these parameters here, the likelihood of getting these data, which we see under observed parameters. And we optimize these parameters here, which are allowed to vary in order to get the highest probability or the highest likelihood of obtaining the data we observe. So the next step but this will be later. We first need to compute other things for our likelihood analysis. So the next step will be to compute the lifetime. What is lifetime? So it's the total number of, total duration of observations. So, okay, first I need to explain, let's say we have our LAT instrument and we observe a source, and how many counts do we get from the source, how many counts the detector will measure. So it depends on the, okay, it depends on the flux, right? It depends on, yes, so somebody wants to ask me. So, okay. Sorry, I didn't notice. So when we handling data, we won't be IPython, sorry, something about IPython. I think it's, I mean, okay. Yes, so about this, yes, so we can, yeah, we can use the Fermi tools. So it's using the specific syntaxes. Okay, I don't know how to explain, but this is more or less based on, so let's say you have a set of tools, and it takes specific input parameters, and you need to, it's like a command line. So there is a line, so you type a command with different flags and different input values, and there is a script, so you can run the script, and yeah, there is a specific syntaxes, and the model file is in XML format. But yeah, you can use IPython. I personally didn't use Python for Fermi analysis, but yes, now, yeah, you can do that. But I won't be explaining Python part because I have no experience. Okay. Yes. Okay. I will try to wrap it up. So there are actually a few slides remaining, just a few slides. So I will try to speed up and we can finish soon. I assume people are tired and you don't really follow it needs to be shown really. We will do that Tuesday, so I will go quickly. So yeah, so the number of counts you get is typically defined by your flux and the lifetime, so the time you were observing, the total time. And very importantly, so it depends on the off-axis angle, so your LAT, so the instrument when it's oriented at the angle, at a slanted angle to the direction of the source, you will get less counts, and this is taken into account by the IRFs. So you need to take into account for these effects. You compute this lifetime cube, so you pre-compute the observational times in order to be able to compute quickly the quantities needed for likelihood later on. So this is so let's go to the next step quickly. Then you compute the exposure from these lifetimes. So I was explaining previously what is this. So these are centimeters square by second. So the quantifying the response. And then we compute the model maps. So what is this? So we take we predict the number of counts based on our model. So we take this model and we multiply it by computed exposure. So how long we were observing and what is the effective area. And we get the number of photons because we specified physical fluxes. We multiply by exposure, we get photons, and we convolve it with IRFs, and we get model counts. And this what has to be compared with the real counts in the data. So this information. So, and this is done by likelihood optimization. So this, for instance, this is how these source maps look like. So these are artificial. So this is what model is predicting for our source, the counts. So this is what is really observed, and this is how the model looks like after we run the source map step. So you can see, okay, it's pretty similar, but the likelihood optimization will tell us the exact parameters. So this is the model prediction for the observation, and the likelihood optimization will tune the parameters to match the data better. So this is, this is one of the final slides. So, and the final step in the analysis, this is the running of the likelihood analysis. So GT-like. Okay, so as I said, the parameters in the file are optimized, and we get our, based on the parameters which maximize the likelihood function, we compute the flux in the energy bins, and like this we get, based on these best parameters, we get the physical fluxes in each bin of energy or time and get our spectra or light curves. And this is the final step of the analysis. So we have this output, and this is the information we are interested in. So, and yes, I would like to finish this presentation with a couple of examples. So how actually the spectra and light curves look like for Fermi. So this is the result from a master's thesis, actually 4 years ago. And so this is for Crab Nebula, so supernova remnant, and pulsar wind nebula. So this is energy in GV. So the logarithm. So this is 1 GV, 10 GV, 100 GV, 1 TeV. So the violet dots is a Fermi LAT spectrum. So it's overlapping with the, so these black dots is the spectrum measured with ISTs, so Cherenkov telescope. So you see they're overlapping. So we have smooth transition. And you see the spectrum is just a power low, but here it has some sort of bump. And so we see interesting feature. And okay, I won't go into details about other measurements. So just an example of what we can get after likelihood analysis. So the same thing for Blazar, Markarian 421. So again, this is Fermi data, the black dots. So we have a power low, and then this is the ISCT data. the same for another Blazer 501. So you see it has a different, harder spectrum, much harder. It means that harder spectrum means that you have more photons at higher energies. So at the end, again, you see that the spectra are overlapping. So it's interesting to combine actually data by Fermi with other instruments, because you want one single composite spectrum to say more about the source. So I have another question. See, you're using different frequencies. Does it mean there are multiple observations? Slide 24. Okay, I think, I don't know, where is the slide 24? 24, yes. Different frequencies. Yes, does this mean? No, it's just the same data selection here. So the question is, I mean, am I using different time intervals or multiple observations to get this? So no, so this is one selection. So after we select the data, this is one selection, but split into 3 energy domains. So 0.11, 110, and 1000. And the same, exactly the same selection, but just split, but just like split into different energy intervals. So all the same observation, but you select photons just in different energy ranges. And so you see quite a different picture because of different instrument response in this domain. And this is useful to, yeah, to make conclusions about the morphology of the source. For instance, you have more gamma rays, like different features and different energies. So you can say something about which processes, like the geometrical configuration associated with specific processes, particle acceleration or whatever. So, okay, I think, so we're gonna wrap it up. So very last figure. So these is examples, there were examples of Fermi LAT spectra. And the final slide, so a light curve. So this is the example of light curve obtained with Fermi LAT, all these dots here. So this is the flare, gamma ray flare of Blazer Markarian 41. Again, one data set I was analyzing. So the flare is when the source flux is increasing by order of magnitude or more. And so you see there is like a flash of gamma rays, and this is the gamma rays collected in the range of 0.1, 100 GeV. And I compare different data. So Fermi LAT data by aperture photometry, so blue dots, and black is the likelihood analysis performed with old instrument response functions. And the green data is the same likelihood, but with newer instrument response functions. So you see they're all overlap. This is essentially the same measurement, but just the likelihood analysis yields you smaller errors. You can see that black or green dots have somewhat smaller errors than the aperture photometry. So this is why the likelihood is preferred. So yeah, I think this is it for today. If you have more questions, just ask me. Yeah, just ask me live. I mean, lively. You don't need to write to chat. So yeah, please. Nobody has any questions? Well, all right. If no more, if you sometime later. If you have any questions, you can ask on chat. I mean, in WhatsApp chat or when looking through slides. And yeah, so next Tuesday, well, we have a lecture on Tuesday, right? So Tuesday, is it 11 or 11 a.m., right? Can you remind me?
Yes, it's 11 a.m.
Cool. So 11 a.m. Okay, so next time we will go through that tutorial for likelihood analysis and try to do it like with hands. I mean, I think, what do you prefer? Because I have Fermi tools installed and I can just do it on my laptop and share my screen and you can just watch, or you prefer, or if you want, because yeah, you need to install these tools and it may I mean, you might need help to do that. So I personally don't know if it will be worth that you install all that. You have to spend some time on sorting out things and then probably you won't need them and you will have to delete them. So is it fine if I will just show on my laptop, like open the command line and just show you the script, the files, try to run something, show you the plots? Will it be fine? Or okay, no answer. I suppose that you're okay with that, and good. So anyway, no, next Tuesday, yeah, at 11 we can do some kind of practical exercise, and yeah. So okay, thanks for. I can stop recording and stop sharing. So thanks everyone, and yes, where is this stop